So hi everyone, I'm Zihua from University of Munich, and I'm working with Heiner and Alice, who are my supervisors, and they're these people who have already helped me a lot for discussing and through the courses of my PhD studies. And so what I'm working on is there are two aspects. The first aspect, the general topic is what Christoph has already introduced this morning, of how the calming of waves introduce the drop of velocity. And they have also similar observations in the field. That is, during the earthquakes, they observed the drop of velocity, and then later on, there's a longer timescale recovery. So the first question I need to answer is there some models that we can use to explain this phenomenon? And the second thing is I'm trying to implement this model into a 2D or 3D solvers so that we can simulate both the lab scale experiments and also the field scale observations. So I will start with the models. So I've been looking through the literatures, and I'm looking for the model that can be used to describe the 2D and 3D phenomenon. And this is the very unique model that I found so far as I know, that can really explain both the softening phase and the recovery phase in a 2D and 3D schemes. And it is proposed by Benjamin in 2017, who have already come to the workshop last year. So this model, in his model, he has this term inside this, the elastic energy of the materials. So this term doesn't come with any physical meanings. So this is one of the unsatisfactory part of the model. So I've been wondering why this term comes from. And I end up into another model proposed by Liakovsky very long ago. It's 25 years ago. And this model considers it was proposed for the static experiment, where they just compress the rock sample with either triaxial or uniaxial test. So this is for studying static loading. And it considers the distributed of cracks that are parallel to each other and are oriented in the direction it is where the maximum tensile or a compressive strain is. But anyway, this model has a very nice feature that can potentially solve the issue. So, but this model originally doesn't have the effect of the softening and recovery, because it doesn't take into account. But I found if we add this difference between the damage phase and the healing phase, we will be able to see the softening in this material in the materials. And in addition to that, if we assume certain level of initial strain, so this initial strain doesn't need to be very large. It can be as small as 1 microstrain or around that value. It already reproduces healing. So this is the model that I found that does come with some physical meanings in terms of the parameters and can also reproduce these both phases. And the next step, I try to compare the model with some lab observations. And this is one of the results from the dynamic acousto-elastic testing that both Niu and Declan was trying to somehow study. So this is in this experiment, they studied both the amplitude dependent and the frequency dependent of the damage. So here, from purple to red to yellow, the frequency is increasing. So we observed not only the damage is increasing with the amplitude, it is also increasing with the frequencies. So this feature can be reproduced by the second model here. And so this is one of the confirmation that we can try to use this model to explain some observations. And the second thing, I implement two of these models in a 2D solver called AxaHive. And here is how the experiment looked like. So it's just stand waves, which is the pumping waves on one part of the sample, and they probe the velocity change in between these two blue sensors. And here is a comparison of the two models with the experimental data. So there's both of the model that explains certain aspects of the data. I will not go into details of how, because I do this also, I use the Markov chain Monte Carlo method to invert for some parameters to see if we can invert some nonlinear parameters from the observations. There are some parameters can be constrained, but there are some other parameters that are less well constrained. We need to combine different setup to really constrain those parameters. And From there, I have some other development in terms of the simulation aspect. So now we can simulate the propagation of waves in 2D in a heterogeneous media in exahype. And here is the simulated damage field perturbed by two scatterers in the sample. So, and I've also tried to implement this model in 3D in SISO, and with some preliminary success. So this is how we reproduce, how we see the this is a recording of the size, velocity size program, and here is the change of damage and the recovery afterwards. And I also have a video here. I hope I can play it. Yeah. So this is how during the propagation of the waves, the damage was developed and heals. And with this slide, I conclude my presentation. So we now have a software that can possibly solve the equations from 1D to 3D with the possibility of modeling heterogeneities and also topography. And the question that I'm planning to answer is maybe we can try to use the heterogeneities media in 2D with the random media theory to study the scattered waves and see how the coda wave really looks like. And the second question, I have an attempt to, maybe we can try to simulate a real earthquakes and to see which aspects of the observation we can explain with the modeling. And that's it. Thanks for your patience.